All right, so today is all about infinite limits and limits as x approaches infinity. So an infinite limit is a limit where x approaches c and f of x, where your output approaches either positive infinity or negative infinity. In both of those cases, our limit does not exist. Right? If it doesn't approach a finite value, we say it does not exist. This occurs at vertical asymptotes. And it would appear I should have given myself a little more space here. All right, but for example, if we're looking at this graph on the right-hand side, so I'm going to just be going up here. So if we're looking at the graph on the right-hand side, if we look at the limit as x approaches 6, f of x, from the left-hand side, well, as we approach 6 from the left-hand side, whoops, we're on this piece and we go down forever. So that limit is going to be negative infinity or does not exist. And then as we come in from the right, we're on the other curve and we're going up forever. So we've got infinity or does not exist. So both of those cases are infinite limits. Cases where we approach positive or negative infinity when our x approaches a finite value. Then we've got the case where we're looking at as x approaches infinity. So this instead is going to be looking at the end behavior. All right, you may be familiar with that term because the end behavior refers to as we go all the way off to the left of our graph and as we go all the way off to the right. So now we're looking at as x goes to positive or negative infinity, what value does f of x approach? All right, so this is a little bit different because instead of it being a finite value, we're going to look at the limit as x goes all the way off our graph, whoopsie, in either direction. So for example, we could look at the limit of f of x, this graph on the left, as x approaches positive infinity, and that would be that pink line I drew there. So we're going off to the right, and it approaches that horizontal asymptote of 3. And then if we go in the other direction, it approaches negative infinity. Then we'd be on the other curve, and as we go all the way to the left, we also approach that horizontal asymptote of 3. So that's the difference between an infinite limit and a limit at infinity. So an infinite limit refers to x approaching a finite value c, and the f of x, the output, approaching either positive or negative infinity. That's going to occur at vertical asymptotes. And then we're talking about the limit as x approaches infinity. So instead of talking about x approaching a finite value, we're talking about the end behavior of the graph. What happens as we go all the way to the right and as we go all the way to the left. So as x gets infinitely large and as x gets infinitely small. So in the case of horizontal asymptotes, that'll approach a finite value. In other cases, we'll be approaching either positive or negative infinity. So rational functions, we have a couple of special cases, 3 in particular. So the part that I didn't include here is g of x cannot equal 0, right? But there's 3 cases, and they talk about the highest degree term. So the highest degree term is in the numerator. Then that's going to, then our limit will approach either positive or negative infinity. It depends on the sign on the highest degree terms. So an example, say we're looking at the limit of x goes to infinity, f of x, where, I'm sorry, r of x is the notation we were using, where the limit as x approaches infinity, we're looking at negative 3x squared plus 2x divided by x minus 1. So the highest degree term in the numerator is 2, right? Is this guy. Exponent's largest than that, and the highest degree term in the denominator is 1. So the numerator has the largest degree term, so it's going to approach infinity, and since it's a negative here and a positive here, that's going to approach negative infinity. But in most cases, we're just going to say it does not exist, right? So what about if the highest degree terms have the same exponent? In the numerator and denominator. Hello. Well, in that case, the limit will approach the ratio of the coefficients on the highest degree terms. So what does that look like? And this basically says that we are going to have a horizontal asymptote at that ratio. So for example, say we're looking at the limit x approaches infinity of r of x, where we've got r of x is equal to that. Our highest degree term in the numerator is the 4th, and our highest degree term in the denominator is also to the 4th. So our limit is going to be 3/5, the ratio of the coefficients on those terms. And we also have a horizontal asymptote then at 3/5. Horizontal asymptote, HA. Okay. And the last case is where the highest degree term is in the denominator. And for that, our limit will approach 0. So let's think about the limit of r of x as x goes to infinity, where r of x is going to be equal to 3x plus 1 divided by x squared minus 10. So here our largest degree term is in the denominator, right? The top numerator has a degree term of 1, and the denominator has the highest degree term of 2. So if you're thinking about as you plug in like really big numbers, like let's say we're looking at 1,000,000, the denominator is growing much faster than the numerator. So a larger denominator means we're getting closer and closer to 0. So for these functions, they're going to end up having a horizontal asymptote at y equals 0. So those are just our special cases for rational functions. They're going to become important on multiple choice and free response questions. So we need to make sure we can at least reason to getting what these three cases are. Now that we've taken those notes, let's look at the actual problems. All right, so we've got some one-sided limits here and some infinite limits that we're going to be talking about. All right. So, with any rational function, when the denominator equals 0, we're going to have a horizontal a vertical asymptote. So for 1, 2, and 3, you'll notice that our denominator equals 0 at x equals -2. X equals 2. So now that we've established there's a vertical asymptote at x equals 2, you can either use your graphing calculator or Desmos.com to construct a graph of this function and use that to talk about what the limit is from the left and the right when we talk about the value of 2, and then also talk about the end behavior as x goes to infinity. So I'm going to use Desmos because I'm on a computer, but you do have those graphing calculators signed out now, so you could use those as well. So you go to desmos.com/calculator, and once you've done that, you type in the function f of x equals into one of the options, and then I put in the asymptote x equals 2 into the other. So once you've done that, we can see that our graph, as we come in from the right, approaches x equal x, as it approaches x of 2 from the right would be this piece. It approaches positive infinity, and from the left it approaches negative infinity. So we can go back to our problems. From the left, negative infinity. From the right, positive infinity. So it does not exist, does not exist. Now we're talking about end behavior. Since it's positive infinity, we're saying as we go off to the right, so graph to the right. We don't need the graph for this though, because this is a rational function. Highest degree term in the numerator and the denominator is 1 for both. So when they're equal degree, it's the ratio of the coefficients. So we've got 21 as our numerator coefficient and 1 as our denominator. So we've got 21. if you were to go back to your graph on Desmos, you would verify that it is indeed 21. All right, next up, we've got power functions. So when we've got a function like this, I'm sorry, exponential functions, not power functions. When we've got a function like this, we should know that it looks like this. So you shouldn't need a graphing calculator to figure that out. However, you could also use Desmos once again. But as we go off to the left, negative infinity, it approaches 0. And as we go off to the right, we're going up forever, so it approaches infinity and does not exist.
When they do desert you?
Tangent x, we should remember, is undefined at pi over 2. So we have a vertical asymptote there. And our function looks like this. So as we come in from the left, we'll be on this one, going up. So that's going to be positive infinity, or does not exist. And as we come in from the left, we're on that other one, going down. So that's negative infinity, or it does not exist. So from the left, we are going up forever, positive infinity. From the right, we're going down forever, negative infinity. All right. Lastly, we've got a graph here. So I don't care so much about your ability to graph this, but let's just go over how you do. So we've got a function where if we plugged in -3, we'd get 0 over 0. This is simplifiable. So you can factor it to x plus 3, x plus 2. And this is a removable discontinuity problem. So this cancels. You have a removable discontinuity at x equals -3. And if you put that into x plus 2, you'll get y equals -1.
To the gym, please.
So we graph our line. It's got a slope of 2, a slope of 1, and a hole at -3, -1. So this is our function f of x. All right, so you don't really need to know how to graph that, but that's how we do it. And we spent quite a bit of time last year on removable discontinuities, so that should seem familiar to us. All right, so as we approach -3 from the left, we approach a y value of -1. As we approach from the right, we approach a value of -1. And since they agree, we've got -1. Whenever we're doing those overall limits, I want you to give the reason for why that's a thing. All right. So if you're doing the homework and you don't give me that reason, I'm going to take off some points. All right, and then we've got as we go to negative infinity and as we go to positive infinity. So negative infinity is our end behavior as we go to the left. So x goes down forever, so that'll be negative infinity. And positive infinity is our end behavior as we go to the right.